In this tutorial, we will try to solve a small problem. So let me read this problem. I think I already explained this problem in lecture 5, but anyway, I will read it one more time. So what we have is like, we have 1000 kg of an aqueous solution. So this 1000 kg of solution contains 50% of acetone. So this is our feed solution. So our feed solution, the weight is 1000 kg, and then out of the 1000 kg 50% is our solute, which we need to separate from water by using chlorobenzene as our solvent. So we are going to use 800 kg of chlorobenzene, and this chlorobenzene is not 100% pure. It contains a bit of acetone, which is your solute. So you are using almost nearly a pure solvent, but it has some trace amount of acetone. We have 0.5% of acetone in this 800 kg of chlorobenzene. So we are performing this in a mixer settler unit, and then after separation so what we do is like we take a feed solution of how much 1000 kg. This 1000 kg contain 50% acetone, 50% of water, and then we add our solvent, which is chlorobenzene. So we add 800 kg of chlorobenzene. Out of this 800 kg, 0.5% is acetone, so some impurities, and then we are going to mix them. And then once we manage to move our solute from the feed solution to your solvent side, and then we allow the system to settle, so that we will get until we get a clear phase separation, so that we can remove our extract and then we can remove our raffinate. So that's the experiment which is done already. So what's the question is like, so they say like this experiment is already done, and we have an extract phase, and then we have a raffinate phase. So we have two phases at the moment. So the question, the first part of the question is like to determine the composition of extract and raffinate phase, and also the fraction of acetone extracted. So what we need to know is how the percentage of solute in the extract, and then percentage of solute in the raffinate. So this is part A, and then part A also contain one more question, which is what's the fraction of your acetone extracted. If you look at here, the solvent already contains 0.5% of acetone, so that acetone will be carried away in your extract side. So we have to calculate ignoring that 0.5% of acetone. So what's the exact mass of acetone extracted from your feed solution? So what's the percentage of acetone that will actually extracted from the feed solution to the extract side? So we need to calculate that one. Yeah. So this is the part A, and part B is we need to calculate the amount of solvent required to if you need to remove 90% of the acetone from the feed solution. So we know that our starting material contains 50% of acetone in our feed. So that will be equal to exactly equal to 500 kgs. And if you need to remove 90% of this mass, or 90% of acetone, so acetone in feed is 500 kg. So if you have to remove 90% of acetone, what is that? It's like 0.9 multiplied by 500 kg. That will be equal to 450 kgs, I think. So if we have to remove 450 kgs from the feed solution, what's the mass of solvent that we need? So that's the question. So we need to calculate the amount of solvent that we need in order to achieve 90% of extraction of your solute from your feed solution to the solvent side. So the first part is like we begin with 800 kg. With 800 kg, what's the percentage of the solute that we get in the extract, and the second part is like we fix some target to the extract. We want extract contains 90% of our acetone from the feed solution. So what will be the solvent that we need? So and what we have is like we have equilibrium data and the corresponding tie lines. So it is here. So this is your aqueous phase, or if you want we can call it as water. So this is your raffinate and this is your extract. So this side is your raffinate side. So we have, instead of percentage, we have the numbers in terms of mass fraction. If you want to express in terms of percentage, all you need is to multiply it by 100 all these columns. So but anyway, for this problem we can stick to mass fraction. So in the ternary diagram, instead of 100 100 100 you will have 1 1 1. So 0.9 0.8 0.7, this will be 0. So this will be 1.9 0.8 0.5 and then 0, something like that. Yeah. So I hope you all can do this. So these are the values we have. So what is water? Water in our case is, so water and acetone, they makes the feed solution. So our feed solution is acetone and then water. So water is nothing but your carrier liquid. Acetone is the solute. And then we are using chlorobenzene as our solvent. So this is our solvent. So we stick to the notations. So for acetone is C, for carrier liquid water we use the notation B, and for the solute, so this is your solute, acetone is C, and then for solvent chlorobenzene, so that's we use the notation B. So we have to plot them, C, A, B. So we have to plot and then we have to generate the tie lines. So I think that's the problem. So what we are going to do in this problem is like I hope you must listen to lecture 5 part 1 before coming to this, before trying to solve this problem. Yeah? So in part 1 we did some mass balance calculations, and then I showed you a list of equations, and I can do it, or I can write it quickly again. Let me check the notes what I wrote before for you. So you must check to your lecture 5 part 1, and also in the PDF I gave you, if you go to, I think it's page number 147, 148, 149, 150. So check those pages. I can see. Check the page numbers. What's the page number? Let me check one more time. 149. Come on, 150. 150, and then 153. So in these page numbers I derived some equation. Yeah, so I will write it. So let me write the simplest equation. Like so this is our extraction unit. You have our feed, so that's our raffinate. So feed, our raffinate, and then you put our solvent, and then this is our extract. So always remember Fx, Rx, and then Sy, Ey. So the mole fraction of solute is X, mole fraction of solute is X, mole fraction of solute in the extract side is Y, mole fraction of solute in the solvent side is Y. So we use some just notations. Yeah, so so we give some number here. So yes, let's put E1 Y1 R1 X1, and then let's call this as S, and then say like what's the notation we used? Let's call this as S1, and this one notation is YS. So S1 YS, E1 Y1 R1 X1. So both X and Y refers to the solute, percentage solute or mass fraction of solute, where X refers to solute in your feed and raffinate. We use the notation Y to refer to the solute, percentage solute or the mass fraction of solute in your solvent and also in extract. So just stick to the notations, if not we will get confused very easily. So this is our extraction unit, or if you want we can call this as a mixer settler tank. So stick to those units, fx r1 x1, can even put the suffix x suffix f, x suffix 1, and so on. And then in the lecture 5 part 2 I showed you how to plot your liquid-liquid equilibrium data on a right angled triangle. So we are going to compile all the things that we learned in lecture 5 part 1 and part 2. So you know how to plot it on a right angled triangle. So I don't remember the page number, but you can check the PDF of the notes. So let me check it quickly one more time. So what we plot here is like XB versus XC. So what is this XB and XC? So let's go back to this table. So I said to you, follow the green line. Follow the green line we have. So this is our raffinate side, and this part on the right hand side is your extract side. So the solute percentage of the percentage of solute in the raffinate side. So we use this notation X, so XC, and then the percentage of your solvent in the raffinate side, we use the notation XB, and then the percentage of your carrier liquid on the raffinate side, we use the notation XA. And if we come to the extract side, we always stick to the notation Y to refer to the in order to give some notation to the solute concentration, or Y refers to your extract side, and then X refers to your raffinate side. So stick to this notation. So whenever we talk about raffinate, we use the symbol X, and then whenever we talk about the extract side, we use the symbol Y. So perfect. So and then the percentage of your solute in the extract side will be, you just put Y for all the extract side, and the percentage of your solute in the extract side we put Y suffix C, and the percentage of your solvent on the extract side we just put Y suffix B, and then the percentage of your carrier liquid on the extract side we use the notation Y suffix A. So stick to these notations, if not it's very difficult to solve this type of problem. If you get confused with what is XA, or if you put XB in your carrier liquid, XA for your solvent side, then you will get a wrong answer, and you will not even you cannot even plot the data. So that's what I mean. So it's going to be very tough. So try to stick to this notation. So it may sound simple, but you must stick to the notations from beginning of your lecture to the end. So throughout our liquid extraction lecture series, we stick to the same notations, CAB, and then X for your raffinate side, Y for your extract side, and then you know what is A, what is B, what is C. So stick to these notations. So how to plot this data? How to plot this data on a right angled triangle? I already showed you in the part 2 of lecture 5. Try to watch it. So all we need to, if you want, I can show one more time. So quickly. So if you see here CAB, so this is equilateral triangle. So we have 100 percentage, 100 percentage, 100 percentage. So what we are doing is like this. We are moving this base to this axis. So let's say we are moving this base to the y-axis here. So just move it here. So what will happen is like your 100 percentage of C will be somewhere in the top, and then your 100 percentage B will be on the right hand side of your triangle. So this point automatically will be 0 percentage of your B, comma 0 percentage of your C. Obviously this point is going still will be 100 percentage A, but we don't have to worry about that. So we just transpose this into a right angle triangle, and this is more than enough. I said to you any point here that will be equal to 100 percentage of, so it will be like A plus B plus C. So if you have any two, that's more than enough to get our phase separation line. So that's what we are having here. So we have our 100 percentage B on the right hand side and 100 percentage C on the top of your y-axis, and then here will be 0 percentage of C, comma 0 percentage of B, comma 0 percentage of C on our axis, and then we will plot in order to get the phase separation line. So how to plot this one? So first we need to plot XB versus XC. So you will get something like that. So you will get your what? You will get your raffinate side. So X, whenever we talk the notation X, it corresponds to raffinate or your feed arm or your feed. And then whenever we use the notation Y, it corresponds to extract or to your solvent. So and if you comma, you plot your YB versus YC, you will get the other side of your phase separation line. This will be your extract arm, and then both will meet at a plate point. Yeah, so we need to plot this one in order to solve this problem. And then let me talk a bit more about your mass balance equation. So this is our equilateral triangle, again CAB. So this is our phase separation line. So this is our phase separation line. So, and if you go to page number, let me check one more time for you. Yeah, if you go to page number 147 of your notes, you will see something like this, F plus S1. So this is we solved in lecture 5 part 1. R1 is equal to M1. I call this one as equation 1, and then we also have Fxf plus S1ys is equal to E1x1 plus E1y1 plus R1x1 equal to M into xm1. I call this as equation, I don't remember what's the equation number. I call this as equation 2. So what does this equation mean? It's like you just take just to follow the red color. So F plus S is equal to M1, and E plus R is also equal to m1. Yeah, so if you plot, I know how to locate your, I already taught you how to locate your feed point here, f, and you also know how to locate your s point here, s1 point. If it's 100% pure solvent, it will be in the corner of your triangle. So you connect them. So if f plus s1 is equal to m1, your m1 point should lie somewhere on, your m1 point should lie somewhere, let me change the just follow the highlighter. So your m1 should lie on this line, somewhere on this line inside the phase separation line. So somewhere here, your m1 will be somewhere here, and then if you look at the other side of your equation, E plus R1 is equal to M1. So if you can plot F and also your S1 line, you can also locate the point. If I give you the percentage of your solute and also your solvent and also your your carrier liquid, you can locate that point very easily on this graph. So it will, if you know the percentage of your extract, say your extract contains okay, how to say, like this is your 100% C, so let's take roughly 50% C is here, this is a 40% C, and then if you talk in terms of your percentage of solvent, it will be somewhere around here, say like 190, 80, 70, 60, say again for say roughly around 50% of your solvent. So if I say my extract contains 40% of solute and then 50% of our solvent, and obviously the remaining 10% should goes to your carrier liquid. So this line will be 10% of your carrier liquid. So we can easily identify, just to follow the blue line or maybe pink line, and just to follow the pen. So this will be our 10%, 10% A, and this line, the pink line which I am drawing now, so that will be 50% of your B, and then this line, that will be 40% of C. So which means you can locate it. This is my extract point. So this point is our extract point. Let me show it in highlight. So that's our extract point. Extract. So this way you can also locate your raffinate, for example. Say like your raffinate lies somewhere here on this point. So follow the highlighter now. So this is your raffinate. Let's assume that's our raffinate point. So what does that point means? Like if you know my raffinate contains, say for example, so this is our, just to follow the highlighter for the moment. So this is our 100% of A. So this will be roughly around 80% of or A. So this point, sorry, so this line will be, I think I missed this page completely. So just to follow the pink line I'm drawing now. So this line will be 80% of A. So, and also if we want, we can also calculate the solute concentration. So this line which I'm drawing now at the moment, the pink line, I will show through highlighter one more time. So this line, so that line will be roughly let's call it as say like 20% of C, for example, comma 20% of C. So from that we can calculate our raffinate point. So maybe let me draw it in the next page to make it clear. CAB. We have to learn this topic by this way, because liquid extraction we design mostly using graphical procedures. So it's okay if I draw bit by bit, and then so that way you will at least understand. If not, it will be very tough, because we are using both graphical method and also some mass balance expressions both at the same time in order to get the correct solution. So F plus S1 is equal to E1 plus R1 equal to M. So that's our equation 1. And then Fx plus S1 Ys is equal to E1 Y1 plus R1 X1, something like equal to Mxm1. So that's our equation 2. So I showed in this in the previous page what I showed, like how to locate your F point, and then that's your S1 point, and then we can obviously locate our extract E point, and then we can also locate our raffinate point, provided we should have all the data in our hand. If we have what's at the beginning of my experiment, I know what is my feed, what is the solvent. At the end of the liquid extraction, I know what is E and I know what is R. So what's the composition of R and what's the composition of extract, which means I did the experiment, I performed the experiment, I finished the experiment, and I even know what's the percentage of A, B, C in the extract side and what's the percentage of A, B, C on the raffinate side. So which means I have every information in my hand. So just to take the first expression, so if F plus S1 is equal to M, so let's draw a line, just follow the green. Maybe let me use the highlighter. Follow the highlighter. So this will be our FS1 line, and then so which according to this equation 1, what it says is like F plus S1, you are mixing somewhere inside the phase separation zone, somewhere from here to here. Your M will be somewhere in this line, but we don't know it. We don't know it, and then we don't know where our M exactly lies. And also according to equation 1, if you look at the other side of the equation, so this one, E plus R1, E1 plus R1, that's equal to our mixing point. So let's call this is E1 and R1. So if you connect these two, let's draw a line, why not? So which means our M, our mixing point, should lie somewhere between this one, under the phase separation line. But since if we know F plus S1 and E plus R1 is equal to M, if you draw this line, they both should intersect at one common point. So that will be equal to M. So this is a graphical method. I think it's called the Hunter-Nash method. I'm just following the notes of my professors. So I maintain my notes, which I used almost like 12 years ago. I'm just following those notes, and then I'm also reading some books while preparing for these lectures. And I studied chemical engineering almost 16 years ago. So that's the line we have. So we know how to identify this mixing point. So and then if we look back into our if you look the equation 2, we have something called as a solute balance. It's the same rule. Fxf is already here, yeah, because we know what's the percentage of solute. So this is our xf line. So this is a 100% solute on the top of your triangle. Follow, maybe let me use a highlighter to explain better. Follow the highlighter. So this is our 100% solute. So this line, so this is our xf line, in fact. So what it says is, oh my god, let me change it to pen. So this line is our xf line. So this is nothing but your percentage solute in feed. Yeah, I hope you all can follow this one. If you think this part is difficult, which mean you haven't seen the lecture 5 part 1 and part 2, you must watch those 2 lectures. Only then this part will become easy for you. Okay, this line looks a bit slanted. It should be horizontal line, yeah. So that's our feed line. And then okay, and what else we need to say? And also, if you draw like if you look at this one, x1 here, x1 in equation 2, for example. So what is that? X1 refers to the percentage or mass fraction of solute in the raffinate side at the end of our experiment. So follow the highlighter now. So go back to this triangle. So follow the highlighter. So this line, so this is nothing but our x1 line. X1 line. So whenever I am talking, you also need to see the screen. Yeah. So this is very liquid extraction is not a easy topic to give lectures, you know, like especially when I'm not seeing you. So I'm if it's in the classroom, I will use the laser pointer, and then I put extra time. I will tell the students like follow the laser pointer, where my pointer goes on this, look at this particular line, this is the line which you are talking about, and so on. And then I will also tell like you draw a line somewhere from the other side of your triangle. I use a lot of laser pointer in the classroom. Sometimes I even take the ruler, like a very long ruler, and then so that I can point the line, which line we are focusing or we are looking into when we're looking at the ternary diagram. But since I'm recording the videos now in the paper tube, you have to follow. Whenever I say follow the red highlighter, follow it. Yeah. So just follow this red arrow which I'm drawing now. So this line is our x1 line. X1 line, where x1 refers to the percentage of a solute in the raffinate phase. Yeah. So I recommend you like at least for liquid extraction and distillation, buy a notebook, buy some pen, try to take the notations of almost everything that you can remember of. Yeah. So and also before your final exam, keep that paper in your hand. Yeah. So when you're going to solve a problem, you should know what is x1, what is xf, what is like xm1, for example, what is y1, so on. Yeah. So keep a track of all the notations that we are using in this lecture. I know we are going a bit slow, but this is completely okay. Yeah? We already covered crystallization very detailed, and liquid extraction we must cover completely, because I think you are not going to study this topic in any other modules. So it's better to go a bit more detailed, and you will use this somewhere in your lifetime if you are working in some pharma industries or even in a chemical industry. So And also I'm going a bit slow because I know some of the students have the habit to to learn through internet resources, which is completely okay. I do that myself. If I don't know, if I don't understand something, if someone put a very nice lecture video, I watch them to get some better understanding. But this topic, liquid extraction and also crystallization, it's very difficult to find a good material in internet. Believe me. Yeah, there are few notes from some universities from in United States, but they are like here and there. Yeah, so it won't order in your flow, and they also have a different notations when they are going to plot it on a ternary diagram. So if you watch one video put by one guy, he will use one notation for solute, solvent, and also carrier liquid, and another guy will use another type of notations, and they will even place the solute and solvent on the other side of the triangle, which will make you very tough to follow. Yeah, so that's why I'm going taking these videos a bit slow, but at the end of the day we will get the desired or expected learning outcome. Yeah? So for the part of liquid extraction, the biggest learning outcome is you know the technique, and then you will learn the ternary diagrams. And ternary diagram is so important not only in liquid extraction, also in many other systems. Even like if you're going to work in future in drug delivery using co-crystallization approaches, then you need to know how the ternary diagram works. Yeah, so it's a very good module, so very good chapter. Yeah, so you will know what's a ternary diagram, how to plot the three different axis in the ternary diagram, and then you know how to convert even those values into a right angled triangle. Those things we learned, and also we learned a bit of a mass balance. Yeah, so without doing without entering into heavy duty chemical engineering topics, we just managed to do the mass balance, like using some simple expressions, and we are also performing some really engineering level calculations. All we have is only one ternary diagram, and we have some feed conditions, we have some solvent properties. We know solvent is pure or not pure, and just with this information we are managing to design a liquid extraction unit. We are trying to find some unknown information that we have to figure it out using just the ternary diagram. Yeah, so that's what we are doing at this moment. So, and also in what we are learning at this moment is like we have one equation, mass balance equation, which is here, and then we have another mass balance equation which is here, and then we are trying to relate it to our ternary diagram. Yeah, so let's go back into the topic. Let's just follow the highlighter again. So I already showed you where is our x1 line, so where is our x of line. So our x of line is here, our x1 line is here. So if that's the case, we can even calculate. If you come to this equation 2, we have this x suffix m1. So this refers to, if you don't remember, so this refers to the percentage of solute in the liquid mixture. So that one we can get on this ternary diagram by drawing a line. Follow the, let's change green, blue highlighter maybe. Just follow the blue highlighter. So that m1 line will be exactly on the mixing point. So the concentration of solute at this point will be equal to, I'm going to use a green pen. So this will be equal to xm1. So this line is our xm1 line. So this is the level of knowledge you should have to solve our problem. Yeah, so So in the problem what we have is, we have our feed. We know what's the percentage of acetone in the feed. I think it's 50%, so this will be like a 0.5 somewhere. And then we have somewhere solvent, which is, this time we have a solvent which is not pure. It's somewhere, it contains 0.005% of acetone. So that will be almost in the bottom of this line. And then 0.995% of what? Our solvent, chlorobenzene. So our S1 point will be here. So we will connect them obviously. So our mixing our mixing point will be somewhere between here and here. So M, we don't know where it is. And we also don't know where is our extract point and where is our raffinate point. So E1, R1, so where is that? Yes, so we don't know. If you go back to, if we have E1 and R1, all we can do is like follow the blue highlighter. We can easily connect them, and then I can tell, oh, this is my mixing point M, and then from there I can even calculate what is our composition XF. Yeah, so if you go back to our question, so where is that? Let me read it out. It's here. Just to follow the, if you look at the part A, follow the blue highlight. In fact, we need to find what's the composition of extract and raffinate phase. So we don't know where is our E1 and R1, because that's part of our question. We need to find this E1 and R1 point. Once if you manage to find that E1 and R1 point on our ternary diagram, so then we can easily calculate the, how do you call it? Let me go back here. So if we know where is our E1 and R1 point, so from this we can calculate X1, Y1. From this we can calculate X1. So always try to remember, so EY RX, FX, and then EY and then SY. So keep this is only to remember which side is X, for which side we use the notation Y. I started to save my videos for every 30 minutes, and then I'm creating a new video, because for some reason my tab always crash for every 40 minutes. So I think I said everything that we need to know to solve this problem. Notes. Yes, I think everything looks fine to me at the moment. So what we need to do is like we have to go back to our liquid equilibrium data. So I said, okay, maybe let me compile what we need to do exactly. So come back here. So what we are going to do, we have our liquid equilibrium data. So we are going to plot them. So we are going to plot to get our phase separation line, and then we will have a plate point, obviously. So plate point is something like your solute concentration in extract and your raffinate will be same. If you come to the table, if you look at here, we know C is our solute. C is our solute. So this, just to follow the blue highlighter. So this is our solute in the extract side, and this is our solute in the raffinate side. And if you see the last point, 0.6058, 0.6058. So what does that mean? The solute concentration, or the percentage of solute, or the weight fraction of your solute in the raffinate side and in the extract side are same or equal. So that's our plate point. So if you plot all these values in your ternary diagram, our plate point will meet at this point, 0.6058 on the ternary diagram, on a ternary plot. Yeah, some of my friends who watched this video, they said I should use the word ternary plot instead of saying ternary diagram. The empty triangle is a ternary plot, and then what we draw on that plot, they said it's ternary diagram. Yeah, so sorry for my very poor English. So let's do this. So what we have is like, let me change color. So we have our feed. We know what is our feed. We know what is our S1 point. So we know how to connect them. All we need is a small scale. We know to connect them, and then just to follow the blue highlighter. Just follow the blue highlighter. So we don't know where is our M point. So where is our M point? We don't know. So we need to find that particular point. So once we find, if we know that point, to know that point, all we need is to know at least one composition. So imagine ternary diagram is so confusing, but it sometimes it's okay to have only one information. I said to you, any point on a ternary diagram corresponds to 100%. But to locate this M point, we need at least the percentage composition of any one of the compound. Say A, B, C, whatever. Yeah. So imagine if we have a imagine if this is our mixing point. In the mixing point, we will obviously will have, say, A, B, C. So the percentage of A will be, say, let's put the word, say like X. A is nothing but our carrier liquid. So B is our X solvent, and C is our X solute. Or all the combination, we call it as X of M1, something like that. So if we know X M1, we can easily calculate, we can easily identify this mixing point. Yeah, especially if you are going to plot the value on something like a 2D diagram, like a right angled triangle. So I will show you how to do that. So all we need is to find, we need to calculate XM1. Where is our XM1? So what is this? This is something like sorry, I think I made a complete mistake. If you come back here, so this XM1, what it refers to? This refers to percentage of solute. Percentage of solute, just this part, your C part. Percentage of solute in mixture. So if we know the percentage of solute in the mixture, so let's plot it here. We know 100% of solute is on the top. So 90, 80, follow the highlighter for the moment. 90, 80, 70, 60, say 50, 40, let's say 30. So our mixing point meets So let's say this is 30% of solute, and that's equal to xm1. So what we identified by drawing this line, we identified where is our mixing point, m1. So, and also if you want we can call it as xm1, this line, the whole line. This is our xm1 line on the ternary diagram. So we know that it's going to intersect on the fs1 line from the formula f plus s1 is equal to m1, or fx of plus s1 ys is equal to m1 xm1. So we know these things. So we know this point will cut at, so your xm1 line will cut, you can, your m or your xm1 line, both are same, yeah, like it will cut. If you are talking about m, that then we know the composition of a, b, c. If you are talking about xm1, which means we know the percentage of solute in that mixture, you know. So if you know xm1, so we can draw this line which is here, and then from that we will get our mixing point. So this is one job that we need to find. And then how to, if we know m1, so if you go back to this page which I draw here for you before, if you come back here, I showed you, like this time follow the red highlighter. I showed you from this Rx line, if we have this extract, if we have this raffinate, then and then it will cut through this mixing point, yeah. So you know this fact. So now what we are going to do is we are going to do the other way around. So what we are going to do in this problem is a bit tricky one. So we have our feed, we have our some s1 line, this is our f, it should be straight line, sorry, and then we have our mixing point which is our m. So now we have to draw a correct tie line, so we have to generate new tie lines, so that should cut across this m point. So we need to generate a new tie line, so that will pass through this point m. So from that new tie line you will know what's the composition of solute on the extract side, E1, and then the percentage of solute on the raffinate side, Y, which is x1. So R1, so this is our E1, from that we can get Y1. So that's the part A. In part A I asked what is x1 and what is y1. So the percentage of solute in the raffinate, and then the percentage of solute in the extract. So what we are going to do now is, like, instead of using a ternary diagram, we are going to repeat everything the same procedure, nothing changed. Only thing is, like, we are going to plot our liquid-liquid equilibrium data on a two-dimensional graph, 2D graph. So you will have x and then you will have y-axis. So this is y-axis, this is x-axis. So what you are going to plot is xb versus xc. You get the raffinate arm, and then we will plot yb versus yc, and then we will get the extract arm. Both will meet at plate point. We will locate our f point, and then we will locate our s1 point. We connect both of them. We will connect both, and then we will calculate xm1. We need to calculate using mass balance expression, and then we will locate. Then the next procedure, we will draw the xm1 line. So from that we will identify our mixing point. mixing point M1, and then we already have some tie lines from our liquid-liquid equilibrium data. So using those tie lines, you have to generate new tie lines. That new tie line should cut through that M point. So just to follow the red highlighter, so we need to generate this new tie line, precise tie line. So that should allow you to calculate E1, Y1, Y1 on the raffinate side. Yeah? So I think we can do this. I think so. What I will do is like I will stop recording video in the paper tube. I am going to show you, probably I will use Panopto. I will show you how to plot your data, and then how to locate your feed point, and then how to locate your S1 point, and then let's draw a line, and then I will show you how to, I think I already showed you in lecture 5 part 2 how to generate tie lines. Yeah, so that's why I showed you before coming to before solving this problem. Yeah, so you have to watch part 2 to know how to generate new tie lines. Yeah, you have to generate a conjugate line. From the conjugate line you generate new tie lines. So you must watch part 2 of lecture 5, then you will know how to generate new tie lines. So and then from that we will calculate x1 and y1, and then we will go on to solve the remaining problems. Yeah, so I will stop now, and then I will continue in my computer. I will record using Panopto. I will show you directly on the Excel sheet. And for your final exam, if you have some problems like this, if you don't want to use a graph paper, just use Excel sheet. So whatever I'm going to show you, just to follow the same technique. Type your data on the Excel sheet, solve it directly on the Excel sheet. Yeah, so I think I said more than enough in order to solve this problem. So this is a very very good problem. Is we have one small problem, but we learned how to we learned a lot, like how to generate new tie lines, how to create a ternary diagram, how to draw a feed line, how to locate the mixing point, how to get and how to generate a new tie line. And we will use that, whatever the thing that we learned, how to generate new tie line using the conjugate line, we will apply that rule in order to solve a real problem. So we will calculate the experimental outcome. Yeah? So if you look at this problem, this is such a beautiful problem. All you have is your initial conditions. So we have something like 1000 kg of a feed solution that contains 50% acetone, and I gave you just the mass of your solvent, and then all we have is the purity of our solvent. And from that, and also we also have a lot of information from the liquid-liquid equilibrium data. From that we are calculating the experimental outcome. So at the end of my experiment, what will be the percentage of solute in the raffinate and in the extract side. So now I will show how to plot your data. So we have our liquid-liquid equilibrium data for the acetone, water and chlorobenzene. So that's a system that we are dealing with. So I already read the problem, still I just copy pasted here what we are dealing with at the moment. So we have something like 1000 kg of aqueous solution, and then 50% of that is acetones, and then we are going to add 800 kg of chlorobenzene. This chlorobenzene contains a bit of our acetone, which is 0.5 mass percentage. So what we need to find is determine the composition of extract and raffinate phase. I already explained this. So I will show you how to, obviously we can plot this data. So what we have here, we have the raffinate side, we have the extract side, and then we have our carrier liquid, and also our solvent and solute on the extract side, and then we have water, chlorobenzene, acetone on the raffinate side. So obviously this is the notations we are using at the moment, ABC, and then we use these notations like XA, XB, XC. X, anything when we start with X, it refers to raffinate side or to your feed solution, and anything that we start with Y, it refers to your extract side or to your your solvent. Yeah, so I think this is fine at the moment. So So extracts, now anything starts with y, that refers to your extract side. Yeah, don't forget this one. Yeah. And then what else? So obviously we can plot. We have C, we have A, and then we have B. So we can plot on a equilateral triangle. But the purpose of this tutorial is to show you. First, we will solve this problem, but you will also learn how to plot it on a right-angled triangle. So I already explained this in lecture 5, part 2. What I'm going to do now is I will just show how to execute it in order to solve some real problem. Yeah? So I can delete this chart. I can create one new. Why not? So as I said to you, for the first thing that we need to plot is let me go back here. So in your x-axis, it should be your solvent. So at the end of your the x-axis, you will have the maximum value of your solvent, which is 1, and then at the top of your y-axis, you will have 1. So 1 corresponds to 100% of your solute. So in the top you have 1, in the right hand side you have 1.0. Let's keep it like that. So what we are going to do is we are going to draw the phase separation line on this 2D chart. Yeah? So we have x-axis and y-axis. So let's plot it. Oops. Okay, let's create a new one. So select data. So first let's cover the extract raffinate arm. So we plot xb on the x-axis, and x-axis we plot our solvent, and then in the y-axis we plot our solute. So this is our whatever we got. So now that corresponds to, we can give a name, say raffinate, and then we are going to plot yb versus yc. So right click, select data, add our x is yb, which is the percentage or the weight fraction of your solvent in the extract side. So that will goes to x-axis, and then the weight fraction of your solute on the extract side, that goes to on y-axis. So we can give a name. Let's call it as extract. So what we got is where is the legends? Let me show. Design, quickly add chart element, legends. So what we have is we plotted the raffinate arm, and then we also plotted our extract arm. We can add a line to that to make it look better, and then we can do the same solid line, smooth. So we have one extract arm, and then you have our raffinate arm on the left hand side. Yeah? So I hope you all can follow this one. So if you want, maybe I can even add axis if you don't remember. So what we have in the x-axis is xb, yb, and what we have on the y-axis is what we have is xc, yc. So that's what we have on the x and the y-axis. So if you plot, we will get the phase separation line. So obviously this point where my cursor is, you see here 0.1376, 0.1376. That's somewhere around here. That's our plate point, and then these two are, if you connect these two lines, that will be our tie line. So let me draw some line. So these two points will be, if you connect them, that will be one tie line. You should watch my lecture 3 or 4, I don't remember exactly, if you want to know what is a tie line. And then we can connect all the tie lines. why not, at least to practice, to know what is our tie line and so on. So that's our tie line. Whatever we are drawing now, that's our tie line. So this is a tie line. This is a tie line. And we have one more tie line. And we have one more tie line. Oops. So these red lines, these are nothing but, we call it as a tie line. And the point on the top, which is here, so that corresponds to our, so this point, that's our plate point. So that's our plate point. So we have raffinate side, we have our extract side. So what we need to do now is like we need to find where is our feed. So let's read the question one more time. So 1000 kg of aqueous solution, blah blah blah, and then we have 50% acetone. So 50% acetone, that's our solute. And one thing clear is our feed doesn't contain any solvent, so no chlorobenzene in our feed. So all we have is 50% acetone, and then which means what does that mean? 50% of acetone in our feed, which means XF, that's equal to 0.5, and then our solvent is 0, which means Y the solvent in our feed is 0, which means the corresponding mass fraction of our solvent should be 0. So let us put that way. So 0% of our solvent will lie on the x-axis. So you see here, this is our solvent concentration. We plotted on the x-axis. So if you want, I can even write it for you to make it clear. So our solvent, or if you want, you can say mass fraction of solvent, that's on the x-axis. Mass fraction of solvent is on the x-axis, and then mass fraction of solute is on the y-axis. So obviously we are plotting mass fraction of solvent in the raffinate arm, mass fraction of solute in the raffinate arm, that will give this blue line, and mass fraction of solvent in the extract arm and mass fraction of solute in the extract arm, that should give this orange line. And we already got our tie lines. We know where is our pinch point, and this type of graph is called a binodal curve, which have one pinch point, and then plate point, and that plate point separate your phase separation lines into extract arm and raffinate arm. So we learned everything so far. So what we have to find is the feed point. Feed point is very easy to find with this problem. So we have our solvent concentration is 0, so that's here. So which means everything that lies on this y-axis, that should be equal to 0% of solvent, and then we have 0.5% of acetone. So that's something here. So if you want, we can plot it 0. .5. I think that should give the so our solute concentration is 0, and our solvent concentration is 0, and our solute concentration in the feed is 50%. 50%, press OK. So that's our feed point. Let me change the color. Let's put it to green and make it slightly bigger so that you will understand where to look. So that's our feed point, which is here. So this is our F point. And then what we need to do now is we have to plot the same, we have to find where is our solvent. If you read the problem, what we have is like 800 kg of chlorobenzene. So that's our solvent. It contains 0.5% of acetone. So what does that mean? Your solute concentration is 0.5%. So that should be equal to, we are expressing in terms of weight fraction, so that should be 0.5 by 100. And then your solvent concentration should be the rest of this value. So it should be 1 minus 0.005. So we can plot that one on this one. Select data, add x is our 0.005. So 0.005 means your solvent is not pure. It contains this quantity, very tiny amount of your acetone. So that's the meaning of that. And 0.995% is your solvent. In this case, it is chlorobenzene. I don't know where this point went. Oh, sorry, it should be the other way around. I did a mistake. Our x-axis is our solute concentration, which is 0.995. Sorry, solvent concentration. X-axis is our solvent concentration. Y-axis is our solute concentration. So press OK. So it's here. So that's our solvent point. So this is our feed point. I hope you all can understand this one. So what we need to do is we need to draw the FS line. So let's connect these two lines. I'm just using Excel, but you can use a graph sheet or anything. I'm just using Excel so that if I ask this question in the exam, you can solve it. So this is our FS line. Whatever the line which this blue line, maybe I can change it to green. So this green, we can call it as FS line. So we already have this point, this line. So now we need to find where is our mixing point. So we need to find the point M. Yeah, it can lie anywhere from here to here, but we don't know. We don't know where that point is. So we need to calculate that value. So that's what we are going to do. So we already derived something. We already derived few expressions based on the principles of law of conservation of mass. So we perform some mass balance for the unit operation for the liquid extraction unit, and then we are going to use some of these expressions to calculate where or to locate where this M point will be on this green line. Yeah, so that's what we are going to do now. So I will go back to my notebook. I will show you in the notebook how to do it. So what we are going to do is like we need to identify the mixing point. So we need to locate the mixing point on the FS1 line. We already showed you on the Excel sheet how to get this FS1 line. So it's a very easy thing to do. So let's try to solve this one. It's not tough. I hope you all remember the mass balance expression. So I said to you F plus S1, that's equal to M1 is equal to E1 plus R1. So this is our equation 1. And then we also performed a solute balance Fxf plus S1ys, that's equal to M1 xm1 equal to E1 so x dot side, so y1 plus r1 is raffinate side x1. So we have these two expressions. From this one we can calculate xm1. So if we have xm1, then we can easily identify or locate the mixing point. Yeah, I will show you how to do that. So let's calculate. So what we have F value. F value is 1000 kg of our aqueous solution, that's our feed. And then we also have S1. S1 is like 800 kg of solvent, 800 kg of solvent. And XF is we have, out of this 1000 kg, 50% is our feed. So 50% is what? 50% is our solute. So we have XF is equal to 50 by 100, so that's equal to 0.5. And then we have YS. So YS is what? YS is the fraction of solute, mass fraction of solute in our solvent, which is going into the extractor. So that's given by 5 by 100. So this is equal to, no, 0.5 by 100. So 0.5% of acetone. So in this 800 kg of solvent, 0.5% is acetone. So 0.5%. So we divide 0.5 by 100, should be equal to 0.005. So that's YS value. So from this one we can calculate XM1. And so if we have F and S1, we can calculate, we can get M1, which is M1 is equal to F plus S1, which is equal to 1000 plus 800, which is equal to 1800 kilograms. So now I hope you all can follow this one, and probably it will make sense now why we did this mass balance calculations before in the part 1 of lecture 5. Yeah, so everything have some reason. So M1 we calculate, from that we can calculate XM1 using equation 2. If you go to equation 2 here, so FXF plus S1 YS is equal to M1 XM1. So therefore M1 should be equal to, we already derived this, so I'm just writing it so that you will get some idea. Sorry, this will be equal to M1 XM1. So XM1 should be equal to, feed value is 1000 multiplied by 0.5 plus S1, what's that value? 800 multiplied by 0.005 divided by whatever the M1 value we have here, 1800 kilograms. So we have this value here. So how to, let me calculate this one. This is a very famous problem. So many people try to solve this one while teaching liquid extraction. So 1000 multiplied by 0.5, and then 800 multiplied by 0.05. Trying to calculate these values. So this should be equal to divided by. So you have a value XM1 is equal to 0.2756. So what is this XM1? This is the fraction of solute in the mixture. So I think so far this is fine. So let's go back to our Excel sheet. So we have, just remember this value, our XM1 value is 0.2756. So let's go back to our Excel sheet and try to locate this point. So we already calculated. So we know XM1, that's equal to 0.2756. So we need to find this line. So what is this one? This is the amount of solute in the mixture. So we know our mass fraction of solute is on the y-axis. So wherever this point, we have to identify this point, 0.2756. So I'm going to use the simple one. So what is this? X is 0, y is 0.2756. You can use your hands. If you are using a graph sheet, you can count like 0.1, 0.2, 0.21, 0.22, 0.23, 0.24, something like that. Since I'm using Excel sheet, I try to use the other way around. So what is this point? So this point will be the how do you call the value x sum 1 line. Yeah, if you want, we can draw a line here. So that will be the x sum 1 line. So let's try to draw it. So let me draw that line. If you are using a normal graph paper, use just a normal ruler and then calculate this line. So there is no harm in that. So what is this line? So this line is our x sum 1 line. Yeah? Oops. So our x sum 1 line. So from this line, this point, so this particular point, so this is the point where this is our mixing point on the FS line. So from this line, we identified where is our mixing point on this FS line. Yeah? So let me try to make this better. I don't know how the Panopto is capturing my screen. I have no clue. I have to replay this video and see how it came out. So what we have, so this is our mixing point. Yes, I hope you all can follow this one. Let's change this to marker to none. So this point is our mixing point. So let me put some marker there so that we will get some idea. So this is our mixing point, which we identified using this graphical method. In fact, this is called the Hunter-Nash method, but anyway, we used some mass balance expression in order to make our life a bit more easy. So what I said to you before, so if you want to know, in the question, if you look at the question, what we ask is like, determine the composition of extract and raffinate phases and the fraction of acetone extracted. So let's answer the first part. So what will be the composition of extract and the raffinate phase? So if this is our mixing point, so whatever the tie line that we get that cuts through this point, so let me take one tie line just for example. This is not the correct tie line. So if we have a tie line, something like 1 and then 2, just imagine if this is our tie line, so whatever the point here, say, and then let me put one more line for you. So if you have any line like that, so this blue line, wherever it hits on the y-axis, that will give the mass fraction of your solute on the extract. And then if you take another blue line which hits in the bottom somewhere here, so this line, so this point on the y-axis, that should give the mass fraction of your solute in the raffinate. So I hope you all can realize the power of ternary diagram. They are really useful. Yeah, like once you identify the mixing point, it also helps you to calculate the amount of your solute, which is that you can find in the extract, and also the amount of solute in the raffinate side. So this is a pure mass balance. So we all know this one, like equation 2, if you remember, fx of plus s1 multiplied by ys, that's equal to m1 xm1. If that equation is true, so whatever we found through this line, that's going to be the correct value. So here I showed it like a, I just randomly draw this tie line. This may not be correct. So how to draw the tie line, correct tie line? So I already explained you in the part 2 of lecture 5. So you have to watch that one. So I can quickly show you how to do that. It's going to be very tricky. Okay, let's keep these two. Maybe let's keep all the tie lines. So all we need to do is like how to draw here. So all we need to do is like draw some horizontal line here, and then another one you have to draw a vertical line from here to here. So just follow the, which color can we put? Just follow the light blue, and it's a very thick line. And then we have to draw a horizontal line. So you do the same one here, and then so and then what we are doing at the moment is we are generating conjugate lines. It might take some time because we need to, I cannot draw quickly here on the Excel sheet. It's making my life so tough. So what we identified here, so now we can, so this is the point, we know our plate point is here, and then we have to connect all the corners in order to get our conjugate line. So I will show you how to do that. It's better to use graph sheet, I recommend you to use graph sheet instead of using this Excel sheet. You will not have time. In graph sheet we can easily draw, and then we will have a better control over the pencil than mouse. Mouse, this is a nightmare for me. So you get something like that, yeah. So what is this? This is called as this line. Now we can delete. Now we can delete this graph, this blue lines, all the blue lines. All these blue lines you can delete. So what we have at the moment, this is called as the conjugate line. So this is our conjugate line. So now we have to generate new tie lines that might pass through this mixing point. So how to generate that? Oh my god, wait a second. So let me keep these two lines. So how to generate them? So let's put something like that. We have to spend a bit of time to generate. That's the only way. So this way we get one tie line here. So it starts from here and then it ends here. Okay, luckily that seems to cut through our mixing point, which is not bad. So that's how we have to generate the tie line. Hope you all get this one. If not, you have to watch this video again and again until you get what I mean. So what we have is like we have a tie line that passes through our mixing point, which is here, and then from that we have this tie line cuts at one point in the extract arm and at another point in the raffinate arm. So from the extract arm we know what will be the solute concentration at that point. so which is roughly on the extract side. In fact, this curve should go a bit up. I don't know. So let's put it like that. So this value will be roughly almost near to 0.3. So this value will be approximately where it cuts somewhere around 0.330 or something like that, and then your y value is 0.25, so somewhere around 0.23. So what does that mean? Or let's go back to our notebook. So I will quickly show to you. So what we calculated from the Excel sheet is so what we calculated from the Excel sheet is like, we put our feed line, we draw our XM1 line, located our feed point, and then we generated a conjugate line. From there we generated our tie line that cuts through this mixing point, and then we have E1 on the right side, R1 on the left side. So we just draw a line here. So that one should give the amount, that one should give Y1, which is nothing but amount or the fraction of solute in the extract. And then you draw a line from here in the raffinate side. So that point should give fraction of solute in the raffinate side. This is nothing but x1, this is nothing but y1. So always remember EY or x. So what will be the correct value? So what, according to my graph, the y1 value is roughly around 0.30, or maybe roughly around 30, something like that, or maybe 3. Let me check one time. I get something like almost near 3.0, something like that, 0.1 or 2, I don't know. So this problem was solved by someone else, and this is the value we got, and that's what I got as well, somewhere slightly above the 0.3 line, very slightly above this line. And then x1 value is 0.236. You might get a slight deviation, yeah, like maybe 0.305 here, maybe 0.234, that's both are okay. So but you have to draw the correct tie line. You should draw the conjugate line. If I ask in the exam, I want to see the conjugate line on your graph sheet. So that's how you get. So what we have, so we answered the part A. In part A, I asked the composition of solute in extract and raffinate. We already calculated. So the composition of our solute in the extract side is nothing but y1, that's equal to 0.302, and then the composition of solute on the raffinate side, this is nothing but x1, which is equal to 0.236. So I think this is good. And then what we need to answer, the second part of the question is what's the second part? Let me check. In part A, what I also asked is the fraction of acetone extracted. In part A, the fraction of acetone what's the fraction of acetone we extracted? So that's another thing that we need to answer.